Electromagnetic radiation consists of oscillating electric and magnetic fields that propagate through space, even in a vacuum. The size of the wave is called wavelength, and how often it comes by is called frequency. The electromagnetic spectrum is the full range of electromagnetic radiation, organized by wavelength or frequency. NASA summarizes it as electromagnetic energy that travels in waves and spans from very long radio waves to very short waves like gamma rays. In a vacuum, all electromagnetic waves travel at the same constant speed, the speed of light. Differences across the spectrum come from changes in wavelength and frequency, not speed. There are two core relationships that tie the whole spectrum together. The first is the wave-speed relationship, where c is the speed of light in a vacuum. The second core relationship is the photon-energy relationship, where h is Planck's constant and E is the energy carried by a single photon. As frequency goes up, wavelength decreases and photon energy increases. These connections are crucial for understanding the basis of the electromagnetic spectrum. Frequency is often more fundamental than wavelength because it directly determines photon energy and remains constant when light passes between different media.
A lot of confusion comes from thinking EM radiation is either a wave or a particle. Actually, light behaves like a wave when you're talking about interference, diffraction, polarization, and imaging. However, it behaves like a stream of particles called photons when you're talking about absorption, emission, and energy transfer at the atomic scale. To put it simply, when looking at a microscopic level, light behaves like waves. When looking at a microscopic level, light behaves like particles.
Visible light occupies only a narrow portion of the electromagnetic spectrum, and from a physics standpoint, it isn't special at all. It behaves like every other form of electromagnetic radiation, following the same physical laws as other waves. What makes visible light important is its relationship to human biology. Human eyes evolved to detect wavelengths between about 400 and 700 nanometers, because this range aligns well with the sun's emission and with the wavelengths that pass most easily through Earth's atmosphere. Over time, photoreceptor cells in the retina adapted to respond to photons in this band, allowing organisms to gather detailed information about their surroundings. Different wavelengths within the visible range are perceived as different colors. This is not because color is an inherent property of light, but because different wavelengths stimulate cone cells in the eye in different proportions. The brain interprets these signals and constructs the experience we call color. Visible light also carries just the right amount of energy. The photons are energetic enough to trigger chemical changes in photoreceptor molecules, enabling vision, but not so energetic that they routinely damage biological tissue, like UV radiation can. We call radiation ionizing if each photon carries enough energy to remove electrons from atoms or molecules, creating ions. Examples include UV, X-rays, and gamma rays. This process can directly damage DNA and other biological molecules, which is why ionizing radiation is considered especially harmful. Radiation that does not have enough energy per photon to ionize atoms is called non-ionizing radiation. This includes visible light, infrared, microwaves, and radio waves. These forms generally interact with matter by exciting vibrations, rotations, or electronic states without breaking chemical bonds.